Have you ever stopped to think about what's actually going on deep inside your phone or your computer? I mean, really think about it? Well, today, we're going to pull back that curtain. We're going to break down the simple, elegant logic that makes all of modern technology possible. We are starting from scratch, from the absolute first principles, to see how we get from a single symbol to a powerful machine. Let's jump in. To make sense of all this, I want you to think about Legos. Seriously, we're going to start with just one single, tiny brick. Then, we'll learn the rules for how to connect these bricks. And before you know it, just by following those simple rules, we'll be building some incredibly complex and amazing things. This analogy is going to be our guide, so keep it in mind.
So, what's our game plan? First, we'll get to know our Lego bricks, the fundamental building blocks of all this. Then, we'll meet the builder, a simple little machine that can follow instructions. After that, we'll figure out what this machine is really good at, and maybe, more importantly, what it can't do. And finally, we'll open up the toolbox and see how we can build even cooler stuff.
All right, first things first. Before we can build anything, we need to understand our materials, right? So let's start with the absolute basics, the raw ingredients of computation.
So at the very, very bottom of everything, we have the symbol. This is our single Lego brick. Think of it as an atom. It's the smallest possible piece of information. A single letter, like A, a digit, like 0. You can't break it down any further. This is it, our most fundamental unit.
Okay, so if a symbol is one single Lego brick, then the alphabet is our entire box of Legos. It's the complete, finite set of all the symbols we're allowed to play with. For example, in the binary world that computers love so much, our Lego box is super simple. It just has two kinds of bricks, zeros and ones. That's our entire alphabet.
Okay, we've got our box of bricks, our alphabet. Now it's time to actually build something. A string is nothing more than a sequence of these symbols, just a line of our bricks clicked together. It could be 101 or AB, it could be really long, or it could be, well, nothing at all. We call that the empty string. Think of it as a clear space on your building table, ready for bricks, but you just haven't placed any yet.
So with our alphabet, we can make all kinds of strings. But what if we only want to accept certain strings? What if we want a set of rules? That, my friends, is where the idea of a language comes in. A language is just a set of strings that follow a specific rule. The rule could be super simple, like all strings must be exactly 2 symbols long. Or maybe it's all valid strings have to start with a 0. A language is simply the complete collection of all the strings that follow those rules.
So let's recap real quick. We start with a tiny individual brick, the symbol. We gather all the types of bricks we can use into a box, that's our alphabet. We snap them together in a line to make a string, and then we create a set of rules for what counts as a valid construction, and that's our language. See how it all builds on itself? Simple, but so powerful.
So we've got our Legos and we've got our rule book. Now we need a builder, right? We need something that can actually look at our strings and decide if they follow the rules. So let's meet our machine.
And this brings us to the big question. How can a simple machine actually read a string of symbols and then make a decision? How does it look at 101 and say, yep, that's valid? Or look at 011 and say, nope, that's not? How does it know?
Well, the answer is a beautifully simple machine called a deterministic finite automaton, or a DFA. And honestly, the best way to think about it is like a board game. The circles are the states. Those are the spaces on our game board. There's always one start state where you begin. The goal is to finish your turn on one of the special final states marked with a double circle. And the arrows, those are the rules of the game, telling you exactly where to move next based on the input symbol.
Now that first word, deterministic, is super important. It means this machine never has to guess. It's not playing with dice. For any space you're on and any input symbol you read, there is only one, and I mean only one possible next move. It's completely predictable. No ambiguity, no choices.
And this table here, this is basically the machine's brain printed out on paper. It's a complete cheat sheet for the rules. It says, okay, machine, if you are currently in state A and you read a 0, you must go to state C. If you read a 1, you go to state B. Period. Every single possibility is mapped out right here.
So, this little machine seems pretty clever, right? But like any tool, it has its strengths and its weaknesses. Let's dig into what it can do and what it absolutely cannot do.
Okay, here is the single most important thing to understand about this machine. It has a terrible memory. I mean, an absolutely awful memory. The only thing it ever knows is which state it's in right now. It has no idea how it got there. Because of this, it's great at recognizing simple, fixed patterns, but anything that requires remembering something, like counting, is totally beyond its abilities.
And this is the classic example where our machine just completely hits a wall. Imagine a language where a string is only valid if it has some number of A's followed by the exact same number of B's. Think AAA, BBB. To check that, the machine would have to read the A's, count them, 1, 2, 3, then it would have to remember the number 3 while it counted the B's. But it can't. It has no memory to store a count. This need for infinite counting is what makes this language non-regular, and it's a perfect illustration of our simple machine's biggest limitation.
Okay, so we know our machine's limits. Now let's open up our toolbox. We have some really cool operations that let us combine languages to build new, more complex ones, all of which our simple machine can still understand. We have 3 main tools. First is union. It's as simple as it sounds. You take 2 languages and just dump all their strings into one big collection. Then there's concatenation, which is like gluing strings together. You take one string from the first language, one from the second, and stick them together end to end. And finally, you have the star operation. This one is the real powerhouse. It lets you take any string from a language and repeat it as many times as you want in any combination.
Okay, theory is great, but let's make this real. Imagine language A has just 2 strings in it, P, Q, and R, and language B has 2 strings, T and UV. Now let's see what happens when we use our tools. So the union is easy, right? We just combine the lists. Concatenation gives us all the possible pairs, PQ with T, PQ with UV, R with T, and R with UV. But look at the star operation on language A. This is where it gets wild. We can pick nothing, which gives us the empty string. We could pick PQ once. We could pick R once. We could pick PQ twice to get PQ, PQ. We could pick R, then PQ. The number of new strings we can make is literally infinite.
And all this leads to a really important idea in computer science, this concept of closure. Think of it like this. If you mix 2 primary colors, you get a secondary color, but it's still a color, right? It's the same thing here. If you take 2 regular languages, 2 languages our simple machine can understand, and you combine them using these tools, the new language you create is also a regular language. Our machine can still handle it. Our toolbox is powerful, but it won't create a problem that our machine can't solve.
So, we've come a long way. We've gone from single symbols all the way to building a machine that recognizes a whole class of languages. But we also found its fatal flaw, that terrible memory. And that begs the obvious question, doesn't it? If this simple machine has limits, what's next? What kind of a machine would we need to build to handle those more complicated problems? Well, that is a story for another day.